Welcome everyone to a new lecture in 4820. So we'll start the lecture now. Today's topic is going to be mainly clustering, but before we start with that, we're going to look at how to evaluate classifiers. So that's something we have from last week. So I'll start with a quick recap of what we did last week, and then look at how we can evaluate classifiers, and then move on to clustering. So there are two main parts of the lecture, and if we have some time left, then there will be a quiz. There are no points on this quiz, but it's just to sort of help you refresh your memory and sort of, make sure that you get everything that we have introduced so far. So last week we introduced these two concepts of supervised and unsupervised learning. So in supervised learning, by now we know that we mean it's a learning process where there is a training data that has been already labeled, and our goal is to learn from this training data to predict the classes, for example, of new unseen objects. In unsupervised learning, we don't have such labels, so we start from unlabeled data. So, which means we also don't have classes, predefined set of classes, and this will be the topic of today. And classification was an instance of supervised learning. And we then built on our understanding of vector space models. So 2 weeks ago, we were interested in representing individual data points in a vector space model. Last week, we introduced how we can actually represent a class of points, again, in this vector space notion. And we ended up having introducing two algorithms that work in what we refer to as vector space classification, which is basically classification and a vector space setup. And so, more concretely, the two ways of class representations were exemplar-based and centroid-based. So, an exemplar-based representation, we don't have an abstract representation, but rather every member of a class is a candidate representative of the class, or you can also say that the full collection of a class members is actually what represent the class. And what is the algorithm that we introduced that builds on this concept of representation? We had two algorithms, classification algorithms. Yeah. Yeah, so nearest neighbor, and then the centroid-based is what we use with Rocchio. In the centroid-based representation, we want to compute an average vector that represents the class. So the what we refer to as the centroid, which is one example of prototypical representation of classes. And other examples were medoids and etc. And then we had also two more or less definitions of what we mean by class membership. So hard membership is meaning that an object can be a member of class or not. So it's an either or, it's a crisp function. And soft membership is this concept of graded membership. So an object could be a member of class A with a probability of 0.4 and class B with a probability of 0.6. So these two membership functions or these definitions will also be relevant to clustering. Yeah, and then the Rocchio algorithm was basically a centroid-based algorithm where so for each class we compute a centroid, which is the average vector of the class members. And one important property of this algorithm was that it's a linear classifier, meaning that it only works with linearly separable classes. The other one was the nearest neighbor, or the k-nearest neighbor, which is an instance-based or an exemplar-based representation where there is no learning whatsoever. It's basically just memorizing all the training examples. And that's, again, the important property of this k-nearest neighbor is that it's a nonlinear classifier. And both learners or both classifiers had their own problems and assumptions, and Rocchio makes assumptions about how the classes are distributed, having spherical shape, etc. And yeah, and we then mentioned this distinction between linear and nonlinear decision boundaries. And so from last week also, we said that vector space classification amounts to computing boundaries in the space that separates the class regions. So we assume that classes are regions in the space, and the classification problem then amounts to basically just computing the boundaries that separate the classes. And and these are what we refer to as the decision boundary. This is an example of how you can draw the decision boundary. But there are, if you just look at it, there are infinite ways of actually how you can draw this decision boundary. So this is just an arbitrary example. So how do we decide which one is the best decision boundary? And if we can decide which decision boundary is the best, then we can decide which classifier is the best. So that's the sort of the introduction to how to evaluate classifiers. So now we want to find a way, an objective way, in which we can decide how good is a decision boundary, meaning how good is a classifier. And this objective way could be as simple as basically counting how many of the predictions a classifier make are correct. So that's basically what we're going to look at today, or in this part of the lecture. And in order to count how many of these decisions are correct, there are actually many ways, and there are many ways in which we set up this sort of experiment in which we evaluate the classifier. But one important component of this is testing the classifier, or the essential component really is testing the classifier on a test data set. So last week we were just talking about training data sets, right? So we said we have training examples, and from them we learn these decision boundaries. And a test data set is a set of examples that are annotated with gold, or with labels, with the true labels. But this set is called test set because we never touch it while we are training. So it's supposed to be, as we say here, it's supposed to be a held out data set. So and the aim of using this data set and having it as held out as not part of our training process is that we want to see whether the model can generalize over new unseen data. So this distinction between training and test data set is the core of basically how we evaluate. Because if you mix them, then you end up with a situation that is not actually sound in the methodological sense. If your test set and training set are mixed, then this is basically just not proper testing. And we also sometimes refer to this test set as a gold standard, meaning this test set, we're going to use it to test, but it's gold standard because we know what is the actual, or what's the true value of an object, the true class of an object. And just why can't we actually test on the training data itself? Do you know why we can't just use the training data to evaluate our classifier? Yeah. Exactly. So we end up with 100% accurate performance. So this is if you imagine you have one nearest neighbor and then you test on your training data set, you're just going to get 100% accuracy. So that doesn't make sense, right? So it's so clear. Typically, in some setups, you would have a third data set called a tuning data set, which is not test and not training. So this data set you can use to tune the parameters or the configurations, which is basically, so you train your KNN or your Rokio on the training data set, and you can test it on this tuning and then reconfigure your parameters. But this is completely separate from the test data set. The test data set is something that we don't touch at all while we are training. Okay, so let's see how we can actually evaluate a classifier. So let's take an example that we can build on to explain the different measures that we're going to use. So let's assume that we have a spam filtering classifier, and these are our training data points. So the points that are in the red circles are the non-spam emails. So these are the legitimate emails. And the points that are in green triangles, or that are green triangles, are the spam emails. So we're giving this data set, and we learned some classifier. Let's say it's Rocchio, and this line here is our decision boundary. So it's a linear, as you can see, it's a linear decision boundary, but that doesn't matter really in this discussion here. And so two things to see here, or so the first thing is the distribution of the data is not balanced. So as you can immediately see, you have many more examples in the non-spam class than in the spam class. So that's what we call an imbalanced distribution of the classes. So that's the first thing. And the second, so which also leads us to saying that we have a majority class and a minority class. So the majority class in this sense is the non-spam emails, and the minority class is the spam emails. And the other thing is we're going to refer to the spam emails or the spam class as the positive class, and the non-spam as the negative. So the positive, because basically our classifier is outputting yes, positive, this is a spam email. So we're going to call that positive, and the non-spam as the negative. And now, since we have learned these distributions or this classification problem, we can introduce our test data set. So these x's here is our test data set. And there are 10 of them, and you can immediately see from just looking at the figure, you can see which ones are going to be classified spam and which ones are going to be classified as non-spam. So everything that is above the decision boundary is going to be in the region that our classifier decides this is spam, and everything that's under the decision boundary is non-spam. So since this is a test data set, we actually know the truth, right? So because we want to evaluate, so we know the actual classes of these points. We know whether they were spam or not, and we can show that by coloring the x's here. So every x that is colored with green is spam in the gold standard data set, test data set, and everything that's colored with red, all x's that are colored with red, are non-spam. So now we have the values of these different sort of points or the actual classes, and we can start to sort of categorize the predictions that the classifier made based on whether they were correct or not. And there are 4 ways in which we can categorize these different predictions. So the first one, these are the four categories. So the first one is true positive. So true positive means that a classifier made a prediction that an instance or an email is spam, and it's actually spam, meaning that it was also labeled as spam in our gold standard test dataset. So positive again is the fact that this is within the spam class, and true is meaning that it's truly positive, and that's it. So this is one way the classifier can be correct. So having a true positive is that meaning that the classifier made the right decision. Now the second category could be the false positive. And the false positive, this is where the classifier made a mistake. And what it means is that the classifier classified an item or an object as spam in our example here, but in our training, or in our test data set, it was labeled as non-spam. So the output was positive, but this output is false. Therefore, it's called false positive. So this is one way in which the classifier can make mistakes. And normally this type of mistakes is referred to as type 1 error. So you can either, you will find it in literature referred to as false positive or type 1 error. The second or the third type of or category of predictions would be the false negative. In this case, our classifier predicted that an instance is negative, in the sense in this example again it's non-spam, whereas in our test data set and the gold standard it was actually spam. So the output is false by being negative, so that's why it's called false negative, and that's also referred to as type 2 error. And the last one is another case where the classifier is making the correct prediction, which is called true negative. So the classifier outputs negative, and it's true, because this is how it was labeled in the test data set. So again, in our example, the classifier outputting that this is a non-spam email, and in the test data set, the label is non-spam. So now we have these different classifications, or 4 ways in which the classifier can be right or wrong. So two ways in which it can be making the correct prediction, and 2 ways it can be making the wrong prediction. Is this clear? So we're going to build on this to make our measures. Yeah. So the first measure in which we can evaluate the classifier is called accuracy. And accuracy is simply the number of correct predictions a classifier make divided by the total number of predictions. So our test data set here consists of 10 X's, 10 instances, 7 of which are correct. So 7 out of 10, that's 70%. So what we do is we sum the true positive and the true negative, the 2 cases in which the classifier is making the right prediction, and then we divide that by the total number of predictions or test instances. Is this a good classifier? 70%? Okay, acceptable? In between? It really depends, right? So you can't tell. I mean, you can't tell this without knowing what to compare to. What is good and what is bad when you say 70%? You need a reference point. And that reference point, in this case, since we have this unbalanced distribution of the data, and we have a majority class, the simplest approach could be to actually assign all the test instances to the majority class. So that's what we call the majority class baseline. So if we actually, instead of doing any classification, we're given this problem, everything that you receive in your email is non-spam, the accuracy would be 70%. So because this true positive, you would lose this true positive, but you would gain this false positive here. So if you assign everything to be non-spam, and then you end up with an accuracy of 70%. So clearly then, this measure itself is not really reflecting the true picture. So 70% is accuracy cannot tell you much, especially, and this is very important, when you have unbalanced distribution of the instances between the 2 classes, as is the case here. So in this case, we turn to 2 other measures that we refer to as precision and recall. So in precision, what we are trying to count is how many correct prediction the classifier made in the positive class. Meaning, how many of the emails that ended up in your spam folder were actually spam. So this is different. Now we are trying, the way we compute this is by dividing the number of true positives by the sum of true positives plus false positives. And recall, the other measure, is refers to how many of the positive examples in the test data set we managed to identify. So how many of the spam emails we managed to identify as spam. Again, this can be computed by dividing by taking the number of true positive instances and dividing that by the sum of true positives and false negatives. So if we put the numbers in now, we see that we have a precision of 50%. So 50% of the instances that we actually classified as spam were non-spam, or were spam, depending on how you look at it. And we only managed to actually identify 33% of the spam emails in our test data set. So now the picture is different. Now we see that, okay, this is probably not a good classifier. So these two measures, you can actually sort of see them as sort of interacting with each other, meaning that you can achieve a higher recall at the price of lower precision. So if you want to achieve a recall of 100%, you can just classify everything as spam, and then you would have managed to find all the positive instances in the test data set. But this means your precision will drop because you will have so many false positives. You will not have any false negatives, so you can get 100% recall, but you will have a very low precision. And this trade-off between precision and recall is important in many problems. So, and which of these two measures is the most important to you will depend on the problem. So, in spam filtering, you can argue that both of them are important. But if you take another application where you're doing classification, let's say you are doing classification for you have a program that helps a doctor diagnose cancer cells, or so you're taking samples of tissues and trying to use this classifier to diagnose cancer patients. And if your recall is, if you don't catch all the instances where patients actually have cancer, that's a big problem. That's a risk. That's a huge risk. So you are willing to actually sacrifice some precision in order to gain higher recall, because you don't mind looking at false positives, but you do mind having false negatives. You do mind actually missing out on some patients that had cancer but were not classified as such by your classifier. So that's where you see the sort of which one is more important. An opposite case or an opposite scenario would be the search engines. So in the search engines, when you're looking for something online, you're not interested in getting all the documents that match your query. You're just interested in the most relevant one. So precision is more important than recall. So there will be very specific, peculiar scenario where you are actually interested in finding all the documents that match a string. What you want is on, typically that's the case, you want your first page of results to be as relevant as possible, even if that means that you're missing out of on some other cases. So and so in some scenarios where both are important to you, then you can use this F-score, which basically combines precision and recall in one measure. So that's the combination of both. Yeah, so this is basically a summary of what I've just described. So you can get 100% recall with terrible precision. So that was for evaluation, basic evaluation for a binary classifier where you have spam, non-spam. But it's often the case that we're working with multi-class classifiers, meaning we're working with classifiers that try to classify documents, for example, into 10 different classes. And then you can't just use precision and recall immediately. You need other measures. One of these measures is macro averaging, which what it does basically is for each class, it computes the precision and recall as we just described, and then computes a global average of them. So for each class, you compute the precision and recall, and then you sum the precisions and divide it by the total number of classes, and the same for recall. However, this has an immediate disadvantage because it will be influenced by the smaller classes. So you'll have different, so again, the situation will be that you won't have equally distributed classes, so they won't be of the same size. Some classes will be small, others will be large, and all of them contribute equally to the total average. So the smaller classes then will have a higher influence in that sense. So you could then do micro averaging if you don't want that effect. Micro-averaging, on the other hand, is basically finding the true positives, and false negatives in all the classes, across all the classes, and then compute one global precision and recall. So you see the difference between the two measures. So in this case, in micro-averaging, the opposite problem will arise, which is basically that larger classes will have higher influence this time, because they will have more instances being true positives, false positives, etc. So you will end up having a situation where the larger classes are actually contributing more to the final precision and recall. So a solution, an in-between solution, is basically to report both of them. So look at both the micro-average and the macro-average, and say this is my final evaluation, and this is how it looks when I do micro-averaging. This is how it looks when I do macro-averaging. So that was it for evaluation. Any questions or anything unclear? It's pretty simple, but that's, as long as you do it in a proper way, then it's really that's what you need to evaluate a classifier. Okay, so to the second part of the lecture is now clustering. So a cluster, just very generally, can be sort of a definition of the word cluster is basically a group of similar things or people positioned or occurring closely together. It's as simple as this. And clustering, when the word clustering means a set of clusters. So cluster is this group, and then clustering a set of groups. And doing clustering and cluster analysis is, again, I mean, everything we do here in classification and clustering, all these kind of things, take root in different disciplines or different fields of studies. And in clustering, you would find it in the early 30s in anthropology and psychology, where scientists were trying to come up with typologies of cultures or individuals in psychology. And they don't have understanding in how to classify this. So they can't just sit down and look at the problem top down, deciding that there exist 3 or 4 types of cultures or individuals. But rather what they do is to try to cluster the groups or the cultures based on some features or attributes, and then look at these clusters. And clustering algorithm then is basically this algorithm that, similar to what we have just said here, would try to group objects based on a set of features that describe each object. So these objects then would be represented as feature vectors, as we did with the classification, and then we will try to group them into different groups where the clusters are where the clusters consist of similar, for some definition of similar objects. We're going to give more proper definitions of what we mean by all of this. But to look at our sort of 2 categorization tasks, again, that in machine learning, so the classification part, which we're done with, again, it's a supervised learning problem, requires label training examples, and our task is to, given some set of examples with class labels, is to train a classifier to predict the class labels of new objects. So that's classification. Cluster, in contrast, is unsupervised learning, and it starts from unlabeled data. And our goal then is to group similar objects together. So in other words, our goal is to uncover or discover the patterns or the sort of the similarities in the data without giving the algorithm any information about what we expect. We don't know, because our data is unlabeled. So what we want from the algorithm is to return a set of groups that are similar. So what we provide or what we give to the clustering algorithm is basically the similarity measure. So the clustering algorithm will need a way to compute the similarity between the objects, and then it will return a number of groups that are similar based on what we what we define as similar. So that could be Euclidean distance or proximity, cosine measure, etc. And overall, our general objective is, given a set of points, we want to partition this set of points into subsets where the similarity among the members of one group is high and the similarity between groups is very low. So what we want is for the members of one group to be as homogeneous as possible, and for the members of different groups in comparison to each other to be as heterogeneous as possible. And some examples of how we can apply cluster analysis in practice. So one immediate way for using clustering or cluster analysis is for data understanding or data visualization, knowledge acquisition, meaning that when you have a large amount of data, the first step in data analysis would be to try and cluster this data. Again, you don't know anything about this data, so you want to understand what groups exist in this data. So, and you don't want to hire someone to go through this data so that you can classify the different instances. So documents, for example, what you would do then is to use clustering, and the clustering algorithm will return different groups, and then you would look at these groups and say, okay, this looks like politics, for example, this looks like economics, etc. Another example where it has been used quite a lot in studying genes, for example. So you have a huge amount of or a huge number of genes, and you don't know how to actually relate them to each other. So you would normally also use clustering, depending on different features, etc. But all of this fall under this concept of understanding or knowledge acquisition. Another area where you can apply clustering is in IR, information retrieval. So this search engine science that we talked about. And you can apply it in different ways, actually. One way is to use it to speed up the search. So if you remember our problem, or the definition of the problem with IR is, you have a collection of documents and you're given a query and you want to find the most relevant documents. So what you would do is, if you represent your documents in a vector space model, each document is a vector, and your query is then represented as a vector, and you compare your query to all the documents you have, and you return the most similar ones, right? So this could be quite expensive to do. So a solution to speed up this process is to pre-cluster the documents, your collection, into different clusters, and each cluster will then be represented by its centroid. And when you are given a query, instead of comparing with all the documents, you compare with the centroids of these clusters. And once you find the most similar cluster, then you compare with the documents that are part of this cluster, and you return a ranked list. So this will cut down the number of computations that you have to do. Another way also to use clustering with IR is to use it when you present the search results. So when you get your results back in a search engine, they could be clustered in different groups. I mean, you can think like discussion forums, for example, are clustered somehow in one group. So these are the results that belong to discussion forums, etc. I'm not sure if it actually it exists nowadays, but at least it used to be the case at some point that you get the cluster of results rather than just sort of a list of things or a list of pages. One important application also of clustering is dimensionality reduction. So this is or a class to achieve class-based features. So this is something that we didn't talk about, but it's actually very relevant to what we did with vector space representations. So what we do with vector space, or what you're doing now with this assignment, is that for each word you're collecting the features, and each word type, each unique word is introducing a new dimension, right? So for each, in the context, so you have target words, and these target words will have context. It's sentences in our case. Each word in these sentences each unique word or word type is introducing a new dimension, and this means that when you have a corpus of 2 billion words, 3 billion words, then your dimensions will be hundreds of thousands. So that's going to be a very, very highly dimensional space that is impossible to work with. So one solution for this is this set of methods that are called dimensionality reduction methods, which helps you reduce the number of dimensions in your vector space representation. And with clustering, you can apply dimensionality reduction by trying to cluster the words in your corpus first before building the vector space representation. So that, for example, all words like things that are drinkable, so wine, milk, water, beer, all of these words would be part of one cluster. And when you build your vector space model, each cluster will correspond to a dimension now. Not each word, but each cluster. So you're looking then into at the context, and you find that you see a word like beer occurring in a context of some word. You can then use this abstract concept that is the cluster itself to be the feature or then the dimension. So this is what, and this is why it's called class-based or cluster-based features. Is that your words are grouped into groups, and whenever you see a member of a group in the context, then it's actually contributing to the feature that is represented as the class or the group itself. Yeah, and so on and so forth. I mean, there are many examples where you can, so news aggregation, that's Google News. You can see it already in product recommendation, market research. All of these examples are actually sort of typical examples of clustering. So I don't think that, there's any point in repeating the many examples here. So we can sort of classify or look at clustering methods and put them in two main categories. One is flat and one is hierarchical. So in hierarchical first, it's or structured clustering is what you're doing is trying to build a tree structure of clusters. So these clusters will be nested, and you will then have a group of, or a tree that is representing your clusters. So two clusters could belong to one parent node, etc. We're not doing that. We're doing the flat clustering. So flat clustering, in contrast to structured, is where you try to decompose a space or the data into different groups, but without any structure. So you basically just have separate clusters in your model. And you can define different membership functions. So as we sort of basically more or less the same as in classification, you have hard clustering and soft clustering, which correspond exactly to what we described in classification. But there's also a third type called partitional clustering, which what we will be working with. Partitional clustering is hard clustering, but we don't allow an object to be a member of two clusters. If you remember, and when we talked about hard membership and classification, we said we can actually allow a member to be allow an object to be a member of two classes, as long as the membership in each of these two classes is hard, meaning there is no graded value for how much of a member this object is. In partitional clustering, this is not the case. It's an either-or function. It's a crisp function, and a member can only be part of one class. One cluster. So there is no multiple memberships here. And again, sort of as we did in classification, we also have this cluster hypothesis, which says, which comes from IR, information retrieval. It says that documents in the same cluster behave similarly with respect to relevance to information need. So information need is your query. So that's what when you say information need in IR. So and what we are saying here is that documents that belong to the same cluster should behave similarly in terms of relevance to information need, meaning that if a document is a member of a cluster and that document happens to be relevant to some query, then we expect the rest of the members in the same cluster to be also relevant to that query. So that's sort of the hypothesis that we make so that this clustering concept works. Yeah, so generally what we are saying then is objects within the same group are somehow more similar to each other than objects in other groups. And that's why we could apply this speed up mechanism where we said that we're going to compare the query to the centroids of the cluster rather than each document, because we are assuming that the members of one cluster are similar to each other and then therefore will be also similar or relevant to the query or the information need. So essentially it's not the same as the contiguity hypothesis that we introduced in classification, but if it helps to imagine that as in classification where we said that members of one class make up one contiguous region in our vector space representation, and these regions don't overlap, you can think of clustering like that also. So to give a more formal definition of what we mean by clustering or flat clustering, so we're given a set of objects O. So this big O is the set of our objects from O1 to On. We want to construct a set of clusters C from C1 to Ck, where each object OI is assigned to a cluster Cj. So each object in our set of objects big O is assigned to one cluster in our set of clusters C. And what you can immediately see here is that you need to specify two things or parameters. One is the cardinality K, which is basically the number of clusters, so the number of items in our set of clusters, and the similarity function in order for the algorithm to work. And even more formally, what we are trying to do is to define an assignment, a mapping, gamma, from the set of objects O to the set of clusters C. And we want this assignment or this mapping or partitioning, we also refer to it sometimes, we want this gamma to optimize an objective function fs of gamma. And the objective function, we'll define it later on, but in optimization problems, you normally have an objective function, a function that you want to either maximize or minimize. And so in very sort of broad and general terms, what we want to optimize, again, we're saying this in different ways now, we want to have high intra-cluster similarity and low inter-cluster similarity. So high similarity between the members of one cluster and low similarity between the members of different clusters among each other. I think, yeah, let's take a break here and then come back in 15 minutes. Okay, so before the break, we just introduced this formal definition or problem statement of clustering. So we're basically looking for a function gamma which assigns each object in our set of objects to a cluster belonging to one of the also clusters that we define in our set of clusters. And we said that our aim is to, for this assignment function, gamma is to optimize an objective function that we will define later. But in general, this objective function is determined or is seen in terms of high intra-cluster similarity and low inter-cluster similarity. So when we define clustering as an optimization problem, we can also approach it as a search problem. So if you think about it, we have a set of points, this big O, and which we want to partition or split or assign to different clusters. And no matter how large, there is actually an infinite number of ways you can actually do this partitioning. So the naive solution or the brute force solution is basically to enumerate all possible assignments, all possible ways in which you can split your data into clusters, into K clusters. So this would give you the set of all possible assignments from gamma 1 to m, and then you choose the one that optimizes your objective function. In this case, our objective function is still not defined yet. We're going to define it. To define it. But in this case, we're just writing here argmin. You can think of this as an operator which looks through a set of solutions, gamma, and picks the one that minimizes the function fs. The function fs is our objective function. So this is the naive approach, but of course, as you can imagine, it can be quite expensive to actually follow this approach. There is an exponential number of ways in which you can actually partition the data into different clusters. So normally in clustering, we would approximate the solution, meaning that we start with a random, some initial random partitioning, and improve it, keep on improving it iteratively until we reach some stopping criterion, some stopping conditions. So there are many things that we're going to define here, but this is the overall idea, is that we define this, just pick a random way in which you split or partition the data, and then keep on improving it. And improving means that you keep on optimizing your objective function. In this case, you want to minimize it. So you keep on doing that until you hit some, or you meet some stopping criteria. So let's talk about this more concretely and within a well-defined algorithm, which is the k-means. So the k-means can be seen as, or it's actually the unsupervised variant of the Rocchio classifier. So its goal again is to, given a set of n observed objects, so we want to partition these n observed objects into k clusters. We'll refer to them as C, big C, so that each point represented by the vector xj belongs to the cluster Ci with the nearest centroid, mu I. So you can immediately see the similarity with Rocchio. So clusters are then represented as by their centroids, and the way we assign objects to clusters is by computing the distance or the similarity to the centroids of these clusters. So an object is a member of the nearest cluster, and the nearest cluster is defined in terms of the distance to the centroid of that cluster. And typically, we assume that we use the Euclidean distance as our similarity function. Again, this is something we know already. So we're just reusing what we learned in a different way. And our optimization problem, or the objective function that we want to learn, is called the within cluster sum of squares. So we want to minimize this within cluster sum of squares, which is basically as written here, it is the sum for each cluster Ci in our set of cluster C, we sum and then for each element within this cluster Ci, we sum the square of the difference between each element within the cluster and the centroid of that cluster. So it's basically looking at all clusters, and for each cluster and each object within that cluster, it computes the distance between the object and the centroid of that cluster and takes the square of that. And this is basically what we're saying here, is we're minimizing the average distance, or the average square distance between the objects and their cluster centroids. Which also could be said in other words, is that we are trying to find a measure that shows us how well a centroid represents the members assigned to the cluster. So if the distance of the members of one cluster is as minimal as possible to its centroid, then that centroid is very representative of the cluster. So this is still not the algorithm. So now we have sort of a general description how we're going to look at clusters through their centroids, and what is the objective function that we want to minimize. So now we can actually start with the algorithm itself. So again, you have the goal again stated up there. It's a simple algorithm. So what we do first is you choose some k centroids. We refer to them k centroid seeds. So you choose them randomly in your space, and then you start your iteration loop, which the first step in this iteration is to assign each object within the data set that you're working with to the cluster with the nearest centroid. And then you compute new centroids for the clusters and iterate again and again and again until you meet some stopping criteria. Since we started by choosing random points to be the centroids, and then we assigned objects to these centroids, to these clusters based on these centroids, the membership in these clusters is going to affect the actual centroid of the cluster. So we'll look at a more visual example. You have a question? Yeah? Yeah, so your question is then... so yeah, so random selection of centroids is... we're going to talk about that, but what you said... So there are many ways of how you can select... so randomly select. So you could say, I'm going to pick a point within my data set and say that this is the starting point, or you can just, as you said, just pick a random point in the space, making sure that you don't pick, if you have k clusters, 5 clusters, making sure that these random points are not overlap or are not the same, so that you don't end up with the situation you described. And as I think as you look at how the algorithm works, you see how when it comes to how the centroid moves, and so it will depend on how the points are distributed. So I think let's try to look at the visual example. Or so basically, yeah, what we're trying to say here is we are iteratively reassigning memberships and recomputing centroids until the configuration stabilizes. So let's have a look at this example here. I'm going to try to use a draw on this. I've never tried it before. So in the top left there, this you have the starting situation where you have these solid points. They are not assigned to any cluster yet. This is where you just started, and you pick these two. Let's see if I can get this to work. You pick these two random seeds to be the centroids. Okay, so these are the two. We are working with 2k here. We want 2 clusters. So that was the first step, randomly selecting. So it could be anywhere else. So let's say it's here. And then the second step, what we did on the graph to the right, is that we computed the distance from the centroids to all the points, and then we assigned these points. So all these lines, you see them connecting sort of centroids to points, is basically counting the or measuring the distance between the objects and these random centroids we select, seed centroids we selected. And basically what we are saying now is that this group of points is the first cluster, and that group is the second cluster. So you look now at the graph at the bottom here, bottom left, and you see that we no longer have solid points, but we have circles and pluses. So we already now identified 2 clusters, but the random centroid that we selected is not actually a centroid for this set of points. So we can now recompute the centroid based on the points that belong to this cluster, and then you will see that the centroid actually moves from being here in this cluster to be in this location. Do you see why that happened? So first it was just a random position, and it happened that all of these points were closer to this centroid than that one. So we said, okay, then this set of points is our first cluster, the plus cluster. And these points are closer to this centroid than the other one. So that would be our second set of points. But this is actually not the average vector. So the seed was not the average vector. It just happened to be closer to them. So what we do then is you recompute the average vector of these. So you recompute the centroid, and it will move to a new position then. And then you apply that over and over and over, and it will keep on moving because the points that were closer to this centroid, by recomputing it, by moving it, became closer to the other one. So over time, then after 9 iterations, the centroid will be here in this position and there. And you can see now that the points that were in the first iteration pluses, now some of them turn to be circles. So this is why it keeps on changing. This is why it's improving. And over time, you can see here how it actually, so this is how, this is just difficult to see. I couldn't find a better visualization. But on the right here, you can see the movement of the centroids. So you can see that with each iteration, it starts to move, and then the movement becomes smaller and smaller until it converges, until it stops. Because then you actually found the cluster of that makes sense to actually represent as one group. Can you link this process with the algorithm? Do you see why it's the case that the centroids are changing? Need to. Okay, so just some properties and also reflections. We still haven't talked about what's the stopping criterion, and how do we start with the seeding or selecting the random initial partitioning. So the complexity of k-means is linear in terms of the number of clusters and the number of instances that we are trying to cluster. So kn. The objective function, which is this within cluster sum of squares, is monotonically decreasing or unchanged, but it doesn't increase for each iteration. Which means, in practice, that our algorithm is guaranteed to converge, but it's not guaranteed to find the global minimum. So what is a global minimum and a global maximum? So since we have this random starting point that every time we start in a different position, and if you imagine this graph here representing the our objective function. So if we by chance start from here at this position here, right? So this is where we start optimizing our function. We picked a partitioning, and we ended up with this value of our objective function. We said that it's monotonically decreasing. So it's going to go in this direction only. It's not going to go up. It's not going to make the clustering worse. It's just going to make it better. So it continues until it reaches this point here, or what we refer to as a local minimum, and it won't continue to the right because, of course, it starts to increase this again. But the problem here is that this is not the global minimum. So if we had started somewhere right here, we could have found a better solution. So that's a problem, because basically you think that this is the best solution, but just because you started from a random or initial partitioning, you ended up in this solution that's suboptimal. And this is a problem for many machine learning algorithms, where you actually end up having being stuck in what we call a local minimum or a local maximum. It depends on depends on your optimization function. So one possible solution for this is to basically run the clustering algorithm so many times, if you can afford that. So you run it so many times with so many different initialization configurations, and then you might actually end up finding the global minimum. But there is also no guarantee that this could happen. And when it comes to seeding, so starting with this initial partitioning, there are several ways we can do this. So several ways we can pick these random centroids. One is to basically look at the instances we have at the data and say we're going to pick k random objects representing the initial k centroids for our clusters. We can also just pick k random points in the space, so just any point. We can pick k sets of m random points and then compute the centroids for each of these sets. So we want k clusters, so we pick k sets of m points and then compute the centroid of each of these sets and say, okay, this is going to be my initial centroid for the clusters. You can also run another clustering algorithm that gives you some clustering and use the centroids of these clusters to be the initial positions for your clustering or the initial partitioning for your clustering algorithm. And yeah, as we said, there's this random nature of the algorithm, which will have an effect on what kind of clustering you get. So depending on how you start and where you start. And as in classification, outliers are troublemakers, because if you remember, outliers are these members in our data where are so different from the rest of the data. So a member of a class that is so far away in the vector space, but it's still a member. So that's why we call it an outlier, a document that's describing one topic, but it's completely different from the rest of the documents in the same class. In clustering, you could have the same problem. You could have outliers, so noisy data points somewhere in the space. You don't want them to affect the way you compute the centroid of the cluster, because they're going to pull the centroid away from the cluster itself. So one solution is to basically say all outliers make up their own clusters. So you can make it a cluster for that, so that to get a proper representation of the clusters. The stopping criteria, so since our algorithm is basically an iterative algorithm that's going to run for some time, so we need to define when it stops. One way is to have a fixed number of iterations. So you can just say it's n times, 10, 20, 50. You can run the algorithm for a fixed number of iterations. Another one, another criterion is to say when the clusters or the centroids don't change, then the algorithm will stop. So if the cluster doesn't change, then the centroid won't change, the members. Another way also to define a stopping criterion is to define a threshold under which the change in the objective function won't matter, and so the algorithm stops. So the difference between the value of the objective function between the current iteration and the previous iteration, and that could be in absolute numbers, it could be a percentage, etc. There are also some variants or close relatives of k-means. One is based on medoids. If you remember medoids from last week, so instead of computing centroids, we compute medoids. A medoid is this representative of the class, but it actually is a member of the an actual data point in our data set, not just an abstract average vector, but it's the vector that has the highest similarity to all other members of the class. So this could be done with the same and with k-means, then would be called k-medoids. We can also do fuzzy c-means. So what we did is this hard membership clustering, but we can also assign soft memberships, and that would be then based on the distance to the centroid of the cluster again. And of course this would affect the way you also compute the objective function, because now the contribution to the objective function would be weighted to the distance from the centroid of the cluster. Yeah, so very quick overview of what's good and what's bad. So about this, the k-means or flat clustering in general. So I assume it's simple to understand, I hope, and it's relatively easy to implement, and it's efficient. So it's linear in terms of number of data points you want to cluster and the number of clusters. So these are the good things. The bad things is that the thing that we mentioned is that this random seeds makes the algorithm non-deterministic. So running the same algorithm on the same data set does not necessarily give you the same result every time you run it. So because you have initial random seeds. So that could be a problem, that you don't get the same result every time you run it. The second issue is actually we have to specify the number of clusters beforehand. And if you remember at the beginning, what we said is we actually do clustering when we don't know anything about the data itself. We don't know how it's what are the relations, how they are, the patterns in the data itself. So we're sort of now saying that we need to specify this k beforehand. So that's a big disadvantage, is that you have to guess somehow that there exist 5 or 6 clusters in your data set, but you don't know that really. The quality of the clusters that you get is inferior to the more sophisticated hierarchical or structured methods. But the structured methods are actually very expensive to work with. So they're less efficient. So it's then again you have this trade-off between quality and efficiency. And again, yeah, so you don't get, so the quality and the information you get from structured clustering is better, and you don't get the same thing in flat clustering. Also reflecting, just to connect things together, so reflecting on the Rocchio, KNN, and k-means algorithms. So in classification we used Rocchio and KNN for classification and k-means for clustering, but as you can see, k-means clustering is basically performing Rocchio classification in each iteration, right? So if you remember, the algorithm is basically we have centroids and we compute the distance to these centroids and say that an object is a member of a cluster that has the closest centroid to it. So that's Rocchio. But in Rocchio we're of course doing classification. Here our aim is different. So that's one thing. So Rocchio in each iteration basically. The other thing is that Rocchio itself, just to think again about this classification, the classification algorithms, Rocchio itself can be thought of as one nearest neighbor. When you think about that, we are actually just comparing to the centroids. So when in Rocchio, we basically what we do is compute the distance to the centroids, right? So that's one nearest neighbor. It's an algorithm that has that you can actually think of it as one nearest neighbor. But that raises the question: is that if it is actually one nearest neighbor, then how is it the case that KNN is nonlinear and Rocchio is linear? Do you see how Rocchio is like one nearest neighbor? Is it clear? And why is it the case then that KNN is nonlinear and Rocchio is linear? Yeah.
I think the number of points, when you have only one point for each cluster, it forms a line and make it basically linear. And when you have a lot of nearest neighbor, this line is transformed in a complex.
Yeah. Yeah. Excellent. Yeah. So that's the point here, is that when you look at the Voronoi tessellation that we did last week, so when you have just one nearest neighbor, when you just look at one instance at a time and one cell here, these decision boundaries between one cell and another are actually linear. But when you put them all together, when you look at all the points in the space, this white line here that goes down, this is the nonlinear decision boundary. So in other words, Rocchio is actually doing Voronoi tessellation. Because if you remember the definition of decision boundaries in the Rocchio algorithm, is this line here that is on equal distance between the centroid of Kenya and the centroid of the UK, right? Which is how we define the cell in Voronoi tessellations also. It consists of all the points that are closer to the center or the point that is in this cell than any other points. So basically what makes KNN nonlinear is that we have more than just one instance or one nearest neighbor. Whereas in Rocchio all we have is one centroid, right? So we don't have any other examples. So we limit our comparison to this centroid. So in other words, again, what we are doing then is basically having just, you can think of it Rocchio as just one cell within this Voronoi tessellation. So it's, yeah, so this is just to basically try and sort of link things together, and just sort of if you see this somewhere, why is there sometimes you could think of Rocchio as one nearest neighbor, even though one is linear, one non-linear. There's this small piece of information that actually what makes KNN non-linear classifier is the fact that you have many different points, many different instances that you compare to. Whereas in Rocchio, it's just this centroid. That's why it's linear. I want to keep some time for the quiz. So I had some comments on this, but I'm gonna leave them. So I introduced 2B last week, and there was some other comments that I wanted to mention, but let's do the quiz. So next week we're gonna have a guest lecturer, so who's going to Andrei Kutsov, who's going to tell you about the modern word embedding models, which are the modern vector space models that are sort of state of the art currently used in research. So for our quiz, I'll just stop the recording. I hope that